Hello, welcome to another Cosmology talk. Today we have Eva-Maria Mueller, who is a postdoc at Oxford University. She'll be talking about the very recent eBOSS/SDSS data release, and in particular, she was in charge of the paper that put all of the analysis together into the Cosmology to give Cosmology results. This is it for SDSS and Cosmology, so what Eva's saying today is essentially the final word on what they know about Cosmology. I'm very excited to have this talk because we're actually recording this just before the paper itself is released, which is something I want to do more of in this channel. So if you've got a paper coming out, please get in touch. Thanks, Eva, for coming and talking. Do you want to tell us a little bit about your work in the paper?
Well, thanks for having me. So the paper presents the cosmological interpretation of the final SDSS dataset release as far as large-scale structure goes. So it is the interpretation, the cosmological interpretation of the clustering using galaxies, quasars, as well as Lyman-α forest from the Sloan Digital Sky Survey, including the results from BOSS, the baryon acoustic oscillation, as well as eBOSS, the extended baryon acoustic oscillation survey. So what we do in the paper, we take the measurements of BAO and the redshift space distortions, the RSD, and we're looking at what are the cosmological implications of these measurements, and just looking at it in a holistic way, putting all the different measurements together.
Cool. So if someone's remembering this talk a couple of months from now, or remembering the paper, and they only remember two things from the whole talk, what would you want those two things to be?
So SDSS is the largest spectroscopic galaxy sample that we have up to date. We have 4 million spectra from galaxy and quasars. And it's the sample with the largest redshift range coverage as well, up to date, covering redshift from 0.1 to redshift of 3. And all of this data is out here now, so you can go ahead and use it. Very soon we're going to make the likelihoods available as well. As far as new results go, now we have a detection of dark energy from BAO measurements alone, without addition of any other data. So just the BAO tell us that we have non-zero dark energy in our universe up to several sigma significance. So there is really no way that our universe is without dark energy. And while we've known that before, we had information from supernova as well as CMB, we now have 3 completely independent probes of cosmology that all hint at the same underlying acceleration of our universe. On top of that, recently we've heard more and more about tension or crisis in cosmology, where we look at the Hubble constant comparing CMB and local distance ladder measurements. And also now with BAO in combination with some information from Big Bang nucleosynthesis, we get an H0 that is in very good agreement with the CMB without using any CMB information, but that is also in tension with the local distance ladder. The paper is about what we learned about cosmology within the last 20 years using data from SDSS from all of the different spectroscopic redshift surveys. So now SDSS had different components. It started off in 1989, so actually I was in high school back then. It started off with the nearby galaxies. You can see that here in green. So really close by, small redshifts. Then later on came BOSS, taking data from 2008 to 2014, measuring luminous red galaxies, so very old galaxies. That covered a redshift range from 0.1 to 0.6. And now very recently, we extended with eBOSS, filling the gap in between that and CMB, going to higher redshifts. For instance, you can see in blue, you have the emission line galaxies, so very young blue galaxies. We have data from quasars, so we're looking at the clustering of quasars, both in the standard clustering way, but also using the Lyman-α forest, so looking at the absorption line of the spectrum. On the right of this picture, you can see an example for each of the different tracers. But in the end of the day, what we're doing with all of these different tracers, we're trying to measure the underlying dark matter distribution, and we're trying to measure the BAO bump. The reason we're doing that The baryon acoustic oscillation is really most of the robust cosmological probes that we have. It is very robust to any kind of systematics, and we can cover a really wide redshift range, as I said earlier, from 0.1 to 3.5 with all our different tracers, whereas supernova is focused more on the very small redshifts or nearby. CMB is from the very distant past. And the BAO can cover a large stretch of redshift range in between that. So here you can see sky coverage of BOSS, eBOSS for the LRGs, the luminous red galaxies, the ELGs, and the quasars. You can see in the NGC and in the SGC, so north and south. And that is really most of the sky that can be observable from one hemisphere. So all of this data was taken, the 2.5 meter Sloan telescope in the Apache Point Observatory in New Mexico. And you can also see that we are covering the same sky with all the different tracers, really allowing us to trace the background expansion of our universe through cosmic time and over the same sky, just with different tracers. So just as a reminder, what is BAO and how we're using it? Is really the basic idea is that we have a preferred scale in the clustering and the distribution of galaxies, the BAO scale. And we can use the scale as a standard ruler in the same way we can use the supernova as a standard candle, just to trace the expansion of our universe through time. But this is not the only probe we have with galaxy surveys. We can also look at the redshift space distortions. So what redshift space distortions, or in short RSD, means, you have the motion of the galaxies by themselves that are distorting our redshift space measurements. So what that means is that along the line of sight, the galaxies appear squeezed and then squished along the horizontal, giving us an anisotropic signal in our clustering that we can use to measure the growth rate of structure. That can give us information, for example, about general relativity. So those are our two main observables, the BAO and the redshift space distortions. But as I said before, in 5 different tracers. So now SDSS has been going on for a long time, and it really has set the mark for cosmology with galaxies up to date. So for example, SDSS had the first detection of the baryon acoustic oscillation signal, seen on the left in the configuration space, so looking at the correlation function. And you can see the magenta line, how that will look without the baryons, and then you can clearly see the bump. To be fair, simultaneously, also people from 2DF did a similar analysis in Fourier space, looking at the power spectrum. But we were first. Similarly, BOSS had the first BAO detection in the Lyman-α forest in 2013, you can see in the left, and also in the distribution of quasars, you can see here on the right, in 2017.
Is the size of the peak rather than just the location of the peak something that is chosen by the model, or is the size something that is a free parameter in the analysis?
So what we're doing is template fitting for the BNO analysis. So we kind of fit for the position, but also allow the shape of the BAO peak to vary freely. So we are marginalizing over that because the shape of the BAO peak can really easily be affected by systematics. What you can see now here, this is our full data set. And in each different redshift, we now have a measurement of the BAO, and we can use this measurement of the BAO as a distance ladder to constrain the expansion of our universe. So on the lowest redshift is roughly 0.15, you can see the main galaxy survey, and then at higher redshift, the LRG, so the luminous red galaxies from BOSS at 2 different redshifts. At even higher redshifts, we have LRGs from BOSS and eBOSS combined, that is part of the new data release, as well as the eBOSS ELGs in blue, the quasars in blue and green, and then the Lyman-α forest at very high redshifts in magenta. And the same here you can see, but now looking at the growth of structure again, and the growth of structure compared to the Planck 2018 lambda CDN best fit model. And you can see our different measurements, again, at low redshifts for the MGS, and then at very high redshifts for the quasars, and in between the LRGs and the ELGs. So overall, we find good agreement with Planck, with a bit of fluctuation, but nothing that is statistically significant. All seem to be in very good agreement internally, but also externally with Planck data. That was the measurements. And you can go ahead and read those 23 papers describing all the details of how the BAO and RSD analysis is being made, and as well as the catalogs, the mocks that are being used to estimate our error bars. But here, this talk is really going to be about what can we learn about cosmology from this data set. What can we learn about the acceleration of our universe? What can we learn about the curvature and massive neutrinos? So that is what my work was all about, was taking these measurements and transforming them into constraints of cosmological parameters and trying to constrain our cosmological model. All right, so now let's go through the paper and look at some of the results. As I said earlier, what I really want you to take away is that we have a significant detection of dark energy with only BAO data. So what you can see plotted here on the x-axis is the matter fraction, on the y-axis is the dark energy fraction, here in a model that allows for free curvature. Keep in mind, if you don't allow for free curvature, then omega lambda would just be 1 minus omega matter, just assuming your normal Friedmann equation. And so here in blue, you can see what we have from BAO, and then in gray, you can see here from CMB temperature and polarization. In particular, here this is Planck, and supernova, this is the Pantheon sample. And you can see it's several sigma away from 0.
Is the reason why you have this information is that essentially you've got the distance ladder at so many different redshifts that you're seeing how it changes in physical distance over time, and therefore it just isn't consistent with something outside of that blue contour?
Exactly.
Okay.
Exactly.
Whereas if you had it at just one, there'd be this huge degeneracy, but because you got it at a bunch of redshifts, it narrows it down.
That is roughly how it was 10 years ago. We can see the BAO was just completely degenerate, just line in this diagram. Whereas now, because we have so many measurements at different redshifts, you're breaking degeneracies. In particular, also including the information from the Lyman-α forests is breaking the degeneracy in this particular plane. So what are some of other findings that we have with our data sets? Well, we can start not just looking at BAO data by itself, but start combining it with Planck measurement. But what else can we learn about our cosmological model? Well, one of the key fundamental parameters is the curvature of our universe. So curvature, it could be flat, it could be positive, it could be negative. And from CMB by itself, you really can't tell. So the CMB by itself has really large degeneracy between curvature and matter. So we cannot really say for sure whether our universe is flat or not. Even adding in the supernova can improve that, but you can really, really nail it down if you combine CMB temperature experiments with the BAO and get flatness of our universe to really high precision. And that statement is actually true independent of whether you want to use Planck or if you want to use WMAP and ACT. As soon as you combine CMB experiments with BAO, there is no freedom for any curvature anymore. The BAO is really good at constraining flat universe. One of the primary drivers for the BOSS and the eBOSS survey was also what can we learn about dark energy. Of course, there are very many different models, but you can usually parameterize it very good just by parameterizing the dark energy equation of state in a constant part, this W0, and then the time evolving part, WA. So here, we're really looking at a very general model for the background, letting the curvature vary, letting W0 and WA vary, and then combine our different data sets. And you can really see how we nail down back to lambda CDM So what we're finding is W0 of -1, WA of 0, and omega K of 0 as well, so flatness. So what that means is that combining all the different data sets that we have up to date, which is Planck temperature and polarization, the supernova, the BAO and RSD, as well as information from the dark energy survey, you can see is that even in this most general model, you're breaking degeneracies. And so we're coming back to a lambda CDM model with a constant dark energy and with a flat universe.
The supernovae being added here, are they the same supernovae that are measuring the larger H0? And if that's true, why can we add that data? Isn't it inconsistent with the CMB plus BAO, or is it a different piece of that data?
Yes, you can say it's a different piece of the data. The supernova, you use the distance modulus, but if you want to transform that into a measurement of H0, you really need to calibrate your supernova. And the way that is done is using these distance ladder techniques, use Cepheids to really anchor the supernova and calibrate them. And then you end up with an H0 that is high compared to the CMB.
So the redshift dependence of the supernovae themselves when they're unanchored is consistent with BAO, but then it's the anchoring that makes it inconsistent.
Yes. But you're bringing up a good point. That are my next slides talking about the where you can see here the results from Reset al. 2019, where you can see you have different measurement. Distance ladder uses Cepheids and supernova, but also some other experiments, late time universe, that give you an H0 that is around 72, 73, whereas Planck really prefers something closer to 67, depending on the model.
Very curiously, the latest holy cow, the TD Cosmo measurement from a week ago, now gets about 67.
Yes, that is not included yet in the diagram.
What's last week's cosmology talk, if you want to hear about that?
So where does BAO fall onto that? So here is a summary diagram of what we can do with BAO when it comes to the H0 tension. So this is a very busy plot, so I wanted to take you through just step by step, going through the different contours. So here the blue is the BAO contour, so BAO data by itself, and the distance ladder is the H0 and the higher H0 value. And what you can see here is that BAO there's really a degeneracy between H0 and RD, sound horizon. And the reason for that being is what we're actually measuring with the BAO is DH and DM. So 1 over the Hubble parameter and the angular diameter distance. So one along the radial direction and in the other one perpendicular to the line of sight. So that really gives us this degeneracy between RD and H0. And in that sense, BAO would be in agreement with both the very high and the very low value of H0. It really depends on what RD is.
And RD is the sound horizon when the CMB formed. So essentially when sorry.
It is the distance traveled by sound waves between the end of inflation and the decoupling of baryons from photons after recombination. Yeah. As a reminder, so if you want to know RD, there are two ways. You could use information from CMB that gives you a constraints on RD. Or alternatively, what we've done here is using information from BBN, from Big Bang nucleosynthesis in particular, we're getting information on the baryon density. So if you look at the equation of RD, implicitly what's in there, there's a dependency on omega BH squared and omega MH squared in here. So now if we do that, is the dark blue is the combination of BAO and BBN. And you can see how the degeneracy is broken compared to the BAO by itself. And you can also see there's a clear tension between the BAO and BBN compared to the distance ladder, the Schultz results, where Cepheids and supernova. Now, here you can see in gray is what you get from CMB. So you can see that BAO plus BBN is in really good agreement with CMB. And keep in mind that here for BAO and BBN, we have really used no information from the CMB. So it's an independent measurement. And we're getting really good agreement between the two. But tension with the distance ladder. So you might say, well, but what you really do is now H0 is kind of a fit, assuming a cosmological model, assuming lambda CDM to kind of trace from very high redshift to H0 of redshift of 0, but you don't really know for sure all the things that are going on there. But you can see here in the magenta, even if we allow for the most general model of curvature, dark energy, so allowing the dark energy equation of state to vary, if you combine CMB, BAO, and supernova, so that is sometimes called an inverse distance ladder, then you end up with an H0 that is around 68. So in very good agreement, again, with CMB by itself.
The pink contours have 3 extra parameters added, and they're still that well constrained.
There's 3 extra parameters, just allowing very generic expansion of our universe when it comes to dark energy. And
that's very impressive how tight the constraints still are. I guess it's a lot of data that's gone into it, CMB plus BAO plus supernova.
Yeah, it's the complementary between all 3 really that we have seen in the previous plot as well, where you can see BAO is really good in constraining curvature. Supernova is really good in constraining WA and also W0. And then put it all 3 together, you get really tight constraint. So what we can say that there is really not much wiggle room trying to explain this tension with any kind of dark energy or modification to the background of expansion of our universe. But now going back to my original plot, you can also do the same spiel, but adding the H0 together with the BAO and then think the other way around. Well, can we constrain the sound horizon? Just using BAO and H0, and we can. And what you can see here is you could rephrase the H0 tension as a sound horizon tension. So taking the low redshift measurements into the high redshift regime, and then getting your constraints on RD. But the tension here really is visible. All right, so what we've seen so far is, on the one hand, we have really excellent agreement with the standard lambda CDM model, but also there are bits and pieces where you're starting to see a little bit of tension. Not everything falls into play as much as we would like to. So the H0 tension is one of these tensions, and where I must say, I am personally a bit more in favor of the low Hubble constant, just because I feel like, no, we have the CMB and we have the BAO plus BBN, so 2 independent and 2 really robust measurements that both want a low Hubble constant. But I might be a little bit biased on that issue as being an eBOSS person.
2 weeks ago, there was a counter argument that, the strong lensing also gets a large H0, but I guess that's kind of gone away now. So, yeah.
Yeah, but the thing is, when it comes to the BAO analysis, it is really, really robust, because it's just really hard to come up with any kind of systematic that would coherently move all of your galaxies kind of in a way that it would move the position of the BAO bump. And also the fitting, having so many data points, is just very, very precise.
And the fact you can get the sound horizon from BBN without even needing to appeal to Planck or ACT or SPT or WMAP. It's just, this is how many baryons there are in the universe, so therefore this is where it should be, is also very compelling, I think.
So the other tension or discrepancy that has been talked about a bit in the past is tension in sigma 8 omega matter plane, or sometimes called the S8 tension. So here, what you can see, as I said earlier, with RSD, we're measuring F sigma 8. So we are measuring the growth of structure. And what you can see here now is, under the assumption of a lambda CDM model, the value for sigma 8 that we're getting from all of our combined RSD measurements. So in red is weak lensing, so specifically this is DES lensing. The dark blue is the CMB lensing, and the gray again is the primary CMB. RSD right now, it's still, the contours are fairly large, in particular in the omega matter direction, but actually our constraints of sigma 8 is not bad compared to the CMB lensing and the weak lensing. And again, in purple, you can see the combination of all the 3 growth measurements that we have. So weak lensing, CMB lensing, and redshift space distortions are all probes that are probing the perturbation and not really the background expansion like the BAO. And you can see that there is a bit of discrepancy, but it's also, I mean, they do overlap.
These overlap, but you said that the red contour was just the dark energy survey, right? And there's also the KIDS and the HSC, I think might be the other one. And they're also a bit lower. So maybe once you added them as independent data sets, the final mauve contour would be slightly lower.
Yeah, it's interesting to see if you compare all 3 of them, where we would end up. And I think that is work that is currently being done, but as far as I know, it's not been out yet.
I think the KIDS are in the process of releasing their data. And if you're interested in that, see the talk by Ben Giblin from 2 weeks ago.
So this was now just results from RSD. If you combine the RSD with the BAO and look at the full SDS data set compared to the full DES data set, so the 3x2, as well as the full Planck data set with primary CMB temperature and polarization, as well as CMB lensing. This is what we're currently getting. So you can see there is a bit of discrepancy between DES and Planck, roughly maybe at 2 sigma. And SDSS is right in between. So you can see in blue the combination of BAO and RSD gives you a constraint in the omega matter sigma 8 and degeneracy direction. There's just an agreement with both.
BAO wouldn't constrain sigma 8 at all, right? Like the amplitude of that peak.
Exactly. It's narrowing down omega matter and all the other cosmological parameters. All right, so unfortunately, SDSS, BAO, and RSD cannot really at this point help with that discrepancy. We are good with both of these surveys. But that's not the only thing you can do with our data sets. You can also look at the sum of the neutrino masses. So we know from particle physics that neutrinos have a mass, but we don't know exactly what their masses are. Now, cosmology is only sensitive to the sum of the neutrino masses. And we have 2 different so-called hierarchies that we're trying to differentiate. So when you have the 3 neutrino species, you could either have 2 very massive and 1 very low mass, or the other way around, 2 very almost 0 mass and 1 that's very massive. So that's the difference between the normal hierarchy and the inverted hierarchy. The minimum mass for the inverted hierarchy is roughly around 0.1. And the minimum mass for the normal hierarchy is at 0.06. So now again, here you can see the effect the BAO has if you include it in combination with Planck. So here in red is the constraints you get from Planck by itself. It's fairly loose, but then there's a massive increase in information when you add in the BAO, and then as well also the redshift space distortions again decrease the uncertainty even further. So that means right now the best constraint that we get for that combination, so for Planck plus BAO plus RSD plus supernova, is right at the edge of the minimass for the inverted hierarchy is 0.099. So it's not significant enough to rule out the inverted hierarchy, but the inverted hierarchy is becoming less and less likely. But we will need more data and tighter constraints for fully ruling out the possibility of an inverted hierarchy.
I think I have a question about a choice of how to analyze the data here, but why is there a negative sum of the neutrino masses allowed in the modeling? Wouldn't you want to just set a prior that it has to be greater than 0?
So the solid lines here is actually the result from our MCMC. Then the dashed line is a Gaussian fit if we allow for negative masses. So our analysis actually did use a prior from 0 to like 5 for the neutrino mass. But then it's also interesting to see if you were to fit like just a Gaussian into it, where would be your best fit and your 2 sigma. And right now you can see that the peak is in an unphysical regime. That's why you also have to be a bit careful your interpretation of the upper limit when it comes to ruling out, because your posterior is kind of in an unphysical region there. All right, so now here's really a summary of galaxy spectroscopic surveys and also what has happened in the past 10 to 20 years within cosmology. So here we looked at a general model where you allow the neutrino mass to vary, the dark energy equation of state to vary, and curvature to vary. And we looked at the different stages in the past. So stage 2 is using results from WMAP, the JLA supernova compilation, and the DR7, so very old SDSS data. And orange is then if you use WMAP, but then include the up-to-date SDSS. So now the final SDSS, you can see how much the error bars are shrinking. For example, when it comes to curvature, but also neutrinos or H0. So this orange is without the Pantheon and without Planck. It's really using the old data, but the new data from the galaxy and quasars and Lyman-α. And then in red, you can see now stage 3 combining all our stage 3 dark energy experiments. So we have Planck, we added in DES, the Pantheon sample, as well as SDSS. And again, you can see how tighter constraints we're getting. Also in this fairly general model where we allow neutrinos, dark energy, and curvature. And again, we're coming back to W of -1 and curvature being 0. So here's a nice comparison how the field has evolved and how much progress we have made in the past 20 years with the galaxy surveys, but also with the other surveys, supernova and CMB. So this is really the conclusion of so-called stage 3 dark energy surveys as far as spectroscopy goes. So we still have the SD3 to come up and a few other things, but as far as spectroscopy is, that is really the final data sets. It's 4 million spectra, it's coming in really wide redshift range. And on top of that, we not only have the BAO, but also the redshift space distortion, the growth rate measurements up to redshift 2.
You said that redshift space distortions constrain this F sigma 8. When you then plot the sigma 8 constraints, have you had to make some sort of assumption on F, like I guess general relativity, and is it the only assumption being made, or is there something else that has to go into that?
No, you do assume general relativity, but other than that, you can calculate your growth of structure. F is being calculated as a function of like the matter content and your other variables.
I feel I have to ask on behalf of people who would want to ask this question. If you look at this with a skeptical enough eye, it does look like the CMB is in mild tension with the supernova and BAO. Is it therefore valid to combine the supernova and the BAO with the CMB to get all the constraints that you do then get when you make that combination?
So I think there are 2 different ways I would think about it. If you're not happy with it, feel free to use WMAP, because there is no tension whatsoever if you were to use WMAP, and none of the conclusions, none of the implication that I spoke to you would change. As far as whether there is a tension or not, so this is actually nothing new. If you've read the Planck papers in 2015 and 2018, it's the same results that we're using here now. My personal point of view is that there is a reason why we call a tension 3 sigma and a detection 5 sigma. And right now, that is a little bit more than 2. So for me, it does not warrant to exclude it. I think 2 sigma is just something statistically that can happen. And you should be very careful when you start to pick and choose which data sets to include and which not to include, just based on maybe what interpretation you would like to have. I mean, look, I'm not a Planck member, and I'm not an expert of CMB, and for sure that there might be some systematic that is unknown to you, but I very, very highly doubt that any of the cosmological implications that I talked about are wrong in any way, because as you said, you don't depend on Planck. You can use WMAP and a combination of ACT and you will end up with the same results. You will end up with flatness, and you will end up with dark energy.
So the next question then is, where to next? I guess you set up the framing for this quite well with your conclusion slide of like, this is the end of phase 3. So what is coming in phase 4? If you want to, you can stick to the spectroscopic stuff, but I guess there's also, Simon's observatory and the CMB sense.
So for me personally, what is first going up is DESI, so the dark energy spectroscopic instrument. It sounds a bit like DES, but it's really a whole different beast. And we started taking data before COVID-19 came along. So now everything is a bit put on hold, which is unfortunate because we were really, really on schedule. But hopefully we can resume that soon. So DESI is, in a nutshell, it's a very, very big BOSS. So it's roughly 20,000 square degrees. Again, measuring the spectra for LRGs, ELGs, quasars, Lyman-α forests, but to a much, much higher precision than it was for BOSS. We will have better constraints on the neutrino mass within, let's hope, 3 years within DESI. But then also you have Euclid, where you have the relensing part, but you also have the spectroscopic component of Euclid. So that's even further in the future and going to even higher redshifts. So that's as far as spectroscopy goes. But as you said, you have the CMB-S4, so stage 4 CMB experiments, as well as yours also has LSST and some other surveys coming up.
And is the stage 4 for spectroscopic surveys just going to be the constraints you've sort of shown today just get tighter, or will things be possible that haven't yet been possible? That we already know of, because obviously there's always unknown unknowns.
Exactly, yes. Who knows? I mean, in a way, part of the reason for eBOSS was really to be preparation for DESI, as a proof of concept that you can use the quasars, that you can use the ELGs, and just to really improving your techniques for your redshift fitter, but all the entire pipeline to basically get ready for DESI. So in essence, I think the core standard analysis would be the BAO and the RSD. But there are also other things that I haven't talked about now that you can do with DESI. So for example, you can look at the scale pinned halo bias to get information on inflation, or you can also look at a cross correlation between the different tracers. You can look at voids, for example. And you can also start thinking about using the full shape of the power spectrum to find more features, inflation, but maybe also relativistic effects and some of these other things. So kind of the key observables in most places will still be your power spectrum and your correlation function, but at much higher precision. So again, I think we're coming in a regime where we can maybe start to differentiate different theories of modified gravity using redshift-based distortions, where right now our error bars are just too large.
All right, so the final question that I ask everyone, outside of your own research, what do you think is the most interesting thing in cosmology at the moment?
The thing is, to be fair, we still don't know the underlying physics of dark energy. We don't understand the physical mechanism of inflation. So even within my own research, there's so many things that are unknown that we hopefully within the next couple of years will get some interesting results.
Cool. Yeah, that's a satisfying answer. Awesome. Thanks everyone for watching. If you like this, please do subscribe and click the bell. It'll allow you to be notified. Leave a comment if you have any questions. And while you're here, you can watch another video. I was mentioning 2 or 3 during the talk, but I'm going to mention another one. It's the second video that we ever recorded on the channel with Session Editor on using all of the kind of data that Eva's been talking about, or at least the previous data, to find voids and analyze voids. And that does break some interesting degeneracies that redshift-based distortions and BAO still have lingering in them that the voids can then add a little bit of extra information on. And other than that, thank you, Eva, for the great talk.
Thank you.